What's up, guys? It's your boy, back with another video. Today we're doing problem number 4 on the final practice exam for controls and dynamics. I'm here with my buddy Matt, and we are trying to solve for controller gains given a phase margin of 60 degrees and a crossover of 10, and an extra little inequality here of root of zp is equal to omega c, which is 10. And so we need to solve first for z and p, and then we will solve for our gain k, which is all inside of this. So we have our open loop transfer function, 10k times s plus z over all of these poles, and our phase margin is 60 degrees, which means that our phase at our crossover frequency needs to be negative 120. And we know our crossover frequency is 10. Now you say, why does it have to be at the crossover frequency? That's because the definition. Phase margin is the amount of, is 180 plus the degree, the phase angle at your crossover frequency. That's the definition. And so 120 has to be at omega c. And so, your omega has, your phase angle needs to be 120 degrees, and that needs to be equal to the sum. You see all this? Yeah, I'll put it over here. The sum of the numerator angles minus the sum of the denominator angles. And you say, how do I find the angles? It's a very good question. What you'll do is you'll take your real imaginary axis and you'll plot each of these terms as a vector. So you have 10k is a fully real and no imaginary. So you're gonna have, a vector goes to 10k, whatever that is. And the angle with respect to the real axis there is 0. And so we'll start off with 0. Now we'll go to s plus z, and we'll say, don't forget s is equal to j omega. That's just the definition. And we can write any imaginary, number in terms of, a plus bi or whatever. So we have, z plus j omega. And don't forget, we're finding omega at omega c, so this will be equal to 10. And so what you can do is you'll go, to z on the real axis, 10 on the imaginary, and you'll go there. You'll say, what is this angle? Well, you can get the angle by doing, tan of whatever that angle is equal to the opposite, which is the imaginary, over the real. And that would be, in this case, the imaginary is 10, which will be the case for all of them, and the real is z. So we can do arctan of this is equal to our angle, and we get, tan negative 1 is equal to 10z. That's your numerator term. Now you'll do minus the sum of all the denominator terms. So you'll get, tan negative 1 of the imaginary term, which is 10, over the real term, which is going to be 1, 5, and p. So we'll do 1 plus tan of minus 1, 10 over 5, plus tan, can you see this? Ooh, not sure. 10 over p. Can you see that? Yeah, just barely. Sorry, my handwriting's not amazing. Now, a good question would be, why is the numerator 10 in all of these? Matt had that question. That's a fantastic question. Because again, you're finding the imaginary over the real. And the imaginary term here is going to be the frequency that we're evaluating at. If I said, find me the phase angle at 100 radians per second, I'm going to put 100 on all the numerators here, because that's the imaginary term. That's s. S is j omega, and the omega is the frequency that we're evaluating at. And so for the crossover frequency, this is the crossover frequency, which is 10. So that's this inequality. You can take this inequality and you say you have two unknowns. You don't know p and you don't know z. But you have this nice little equation right here. Root of zp equal to 10. You can square both sides and you can say z times p is equal to 100. Now, this is a very easy spot to mess up. I myself messed this up when I recorded this video, and I have to record it again. This is very sad for me. I had a very good video. I did all in a couple takes. It was great. But when you do this, you have to be very careful, because you can say, z is equal to 100 over p, or you can say p is equal to 100 over z. But because we are creating a lead compensator, it tells us that in the question. It says, and a lead compensator, we know that our P must be greater than our Z. That is the definition of a lead compensator. A lag compensator has a 0 first, which means that we're going to have less of a response at the higher frequencies, and a lead compensator will have a greater response at higher frequencies. So we need to have our pole greater than our 0. So all that to say, you need to have P is equal to 100 over Z because we know P is greater. I don't know how else to explain that. If you made the mistake of doing Z is equal to 100 over P, which is a valid way to solve this, if you don't have this extra inequality, you will end up getting the correct answer but flipped. You'll get the correct answer for P as your Z and Z as your P. And that should throw a red flag for you because you'll get a higher Z than a higher P. And so it's just important to make sure you remember to reevaluate your pole and your 0 to make sure you're satisfying the lead or the lag condition. And so if you do solve it the way I did in the last one, where Z is equal to 100 over P, you're actually going to get your pole and your 0 flipped for the values. You'll get like 6 for P and 16.5 for Z. And then you should be like, oh, that's wrong. It's the other way around because you know this. And it still works. Important to note. Anyway, now that you did that, you can throw this into, you can do P is equal to 100 over Z, plug it into here, do a one-term algebra on your calculator, you'll get the correct values. And now it's time to evaluate for K. You need to know the magnitude. I'm just going to pause here. We're back. Okay, so we need to now figure out K. And what's cool is that we know we're at our crossover. We know our crossover frequency, and we know everything except for K. And what we know also is that at the crossover frequency, our magnitude is equal to 1 or 0 dB. Those are equal to one another. Why is that? When you look at your Bode plot at 0 dB, this is your dB, this is your frequency. Your equation might look like that. It might look like this. Your omega c is when it equals to 0 dB. In 0 dB, you can say 0 is equal to 20 log 10 of x, and that would give you your magnitude. This is equal to 1, I'm pretty sure. Let me double check. That would have been so embarrassing if I was wrong. I was correct though. Okay, so we know our magnitude has to be equal to 1 because that's the definition of crossover frequency of when you're in 0 dB, your magnitude is equal to 1 or 0 dB. This is the decibel equation. Anyway, so we now need to figure out what is our K value given our magnitude equal to 1. So you have 1 is equal to, magnitude. Can you see all this? Great. So your magnitude equal to 1 is equal to what? Well, let's first evaluate, like we did last time with angles, 10K. What's the magnitude of that vector now? Not the angle, just the magnitude. That's super easy. It's just 10K. Great. We have 10K times. Well, what's the magnitude of S plus Z? Well, what is Z?
Z is going to be 6.04.
And like P is like 16?
16.55.
Great. So we know S plus Z can be also written as Z is 6, we'll just say 6, 6.04, plus J omega, which is 10I, J or I, whatever, 10I. So this is our, vector, and we can just do Pythagoras theorem to get the magnitude, which is, 6.04 squared plus 10 squared, which is omega c. And this is just like this is z, or whatever this term is right here. And so put that here, say 6.04 squared plus 10 squared, and then we put it over, now we have the root of 10 squared plus 1 squared times the square root of 10 squared plus 5 squared times the square 10 squared plus our pole is 16.55 squared. Boom! You took this, I got all this from over here, right? 1, 5, and 16.55. 1, 5, 16.55. And all of them is 10, again, because that's going to be your imaginary axis magnitude, because that's your crossover frequency, or the frequency we're evaluating at, and it's equal to 1 at the crossover frequency. Now, when you plug this in, you solve for K, you end up getting the correct answer of like 18.6 or whatever it is. What is it? 18.6, look at me go. Anyway, that's how you solve it. what you first do is you say, I know my phase angle at crossover frequency because I know my phase margin. That gives me my z and my p. I know my z, my p has to be greater than my z. So no matter what I get, I know that whichever term is greater has to be p. The smaller one has to be z. Now you find your magnitude, which is everything is solved for except for k, has to be equal to 1. So you know that you find your magnitude by finding the magnitude of the vector. And you find the angle behind the angular vector on the imaginary real plane because we know s is equal to j omega. And the omega is the omega you're evaluating at, and because your crossover frequency is at 1 dB, you know your magnitude, and you know your phase angle. Yeah, boom! Good luck in your exam, beat the hell out of exams, and yeah, like, comment, subscribe, tell your family, tell your friends, and a special thank you to Mr. Matt. Peace.